Swayam Prabha. Digital India. Educated India.
Hi everyone, welcome again to the course of structural biology. We are continuing with structural biology techniques. In the last class of the module of cryo-electron microscopy, we start with generalized idea about microscopy. We have introduced cryo-electron microscopy, but talk more about light microscopy, electron microscopy, some history and detailing of electron microscopy. Today, we will come to the topic directly, for which we are making this module, the cryo-electron microscopy. Cryo-electron microscopy could be divided in two parts: cryo-transmission electron microscopy and scanning cryo-electron microscopy. The original one, the original cryo-electron microscopy comes through cryo-electron transemission microscopy. The cryo transmission electron microscopy, it could be divided into two parts. One is single particle and another is cryo-electron tomography. We will talk about them when we will go to the instrumentation. So, as I told, it is a modified form of transmission electron microscopy, and it can be used to provide structural information on a range of biological specimen from cells to macromolecules. This is very important when we are talking about X-ray crystallography. X-ray crystallography is specific for DNA, RNA, protein and viruses. NMR have many dimensions. They could be used to identify small molecules, they could be used to identify secondary structures. There are so many different type of experiments. They could even be employed for dynamics. They could also use for getting the metabolic profile, and there are many uses as we talked about. Here also in cryo-electron microscopy, they could get the details of a cells and relatively larger assemblies. Even in macromolecules, cryo-electron microscopy is not good for small proteins, they are good for bigger assemblies. We will talk about them. The resolution of the information that can be acquired using electron microscopy is dependent on the properties of the sample, the specimen preparation method used, the technical specification of the electron microscope and imaging parameters. So, properties of the sample is one determinant, specimen preparation method. We will talk about technical specification of the electron microscope and imaging parameters. 3D information can be obtained from 2D electron microscopy data collected in various ways, including single particle analysis, which I talked about, helical reconstruction, electron tomography with or without tomograph averaging and 2D crystallography. These methods of data processing are suitable for different samples. Single particle analysis for purified homogeneous protein complexes, mostly the work done with ribosome, nucleopore system, we will talk about them. Helical reconstruction for protein assemblies with helical symmetry such as microtubules, tomography for unique assemblies such as organelles and cells, and 2D crystallography for protein significantly smaller than 150 kilodalton that form ordered 2D arrays such as bacteriorhodopsin. So, the crystallization, when they are not forming a 3D crystal, by 3D crystal I mean when they are not forming this. this axis, they are only forming a flat crystals. This is a 3D crystal and this is a 2D crystal. So, 2D crystal also could be solved by using cryo microscopy. Single particle analysis uses multiple untilted 2D projection images that contain many single particles with different angular orientations. So, you have collected different images with different angular orientations, you have to work on them. The angular relationship between each view of the specimen can be calculated in the images to provide the 3D information. Electron tomography and 2D crystallography obtain different angular views by tilting the same specimen many times, typically tilting the specimen between plus minus 65 degree and taking an image every 2 degrees, yielding 65 images of the same area. The angular relationship between each image is known because the tilt increment is defined, and so this can be used to reconstruct 3D information. We will talk about these in details in the data analysis section. The generation of 3D structural information from 2D micrographs and electron diffraction patterns using the processing methods above has been reviewed extensively. Other places we will mostly focus on the general simplified method and its derivative. Here, steps towards biological structure determination by electron microscopy are discussed with a focus on sample preparation and imaging of specimen for single particle analysis and electron tomography, although many of the concepts and considerations we have discussed are applicable to generalized other systems. So, let us first take a look at the whole procedure by which a cryo-electron microscopy works. First, you have a sample, then you have to stain the sample with a negative stain for the visualization. So, you take the sample, you do the negative stain and you visualize it. Then you go for cryo-EM visualization. You make the optimization of the grid. Grid is the platform we will talk about where you will put your sample. Then you will do the cryo electron microscopy data collection, and ultimately you will do cryo EM reconstruction on superior microscope, high resolution microscope. So, this is the basic steps: sample, negative stain visualization, cryo electron visualization, then grid optimization, cryo electron data collection and data reconstruction. But this is if the sample appears reasonably homogeneous. Homogeneity is a very critical component of successfully making this experiment. Now, you could directly go without doing negative stain, you go to cryo EM visualization directly. You could also make negative stain reconstruction and then go to cryo EM visualization. If your sample aggregate or it is heterogeneous or it is not well distributed on the grid optimization for staining or the sample. So, what are the conditions? If your sample would be aggregated, if it get aggregates, if it is not homogeneous, it shows heterogeneity, if it is not well distributed on the grid, if your staining is not optimized or your sample need to be optimized. So, many condition, then you have to check them in grid optimization state before the data collection, go back to the sample, prepare the sample again and come back. Also, from cryo electron data collection, you could go for single particle reconstruction and then you could do this cryo electron microscopy reconstruction to go for single particle reconstruction. So, we will talk about the procedures like the sample preparation, negative staining, visualization, grid optimization and data collection in this class. Coming to sample preparation. When generating a specimen of imaging by electron microscopy, the ultimate specimen preparation technique may influence consideration at the sample preparation or purification stage. To perform single particle electron microscopy, thousands of identical particles are imaged and computationally averaged together. The ideal single particle specimen is thus as homogeneous as possible. Heterogeneity can result from both conformational variation and flexibility or by compositional changes such as the presence or absence of different subunits or binding partners. So, if you are going to construct scenarios where you have a complex, you know these guys are making these complexes and you want to see that in absence of, like you have 5 units or 5 binding partners and one is big enough to start with single molecule electron microscopy. So, you put molecule A and then you add B, then you add C, then you add D, then you add E. So, in that way there would be changing composition of the subunits, binding partner, changing the homogeneity of the solution. This is not good for single particle electron microscopy. If you have to do single particle electron microscopy, you have to make a stable unit and then use this homogeneous unit. Compositional variation can be reduced biochemically using appropriate protein purification method. We have talked about different purification methods, we have talked about affinity chromatography, size exclusion principles, we have already talked in their details, and we also talk about ionic chromatography. So, these are different methods we have discussed in detail in X-ray crystallography. I am not repeating them, but you have to go through and you have to apply the appropriate protein purification method. Although a biochemically pure sample does not ensure the sample will appear homogeneous. So, how you know a biochemically pure sample? You will run in the SDS gel, right, and you get a pure band. So, you know it is pure protein, but when you do silver staining, you will see that this protein is not so pure. So, your biochemically pure definition might not make it actually pure, point 1. Point 2, it might have different conformations. So, when you are putting it into SDS, you denature the protein by applying SDS, boiling it and all, it shows one band, but in actuality it have different conformations. So, many things are possible. Structural arrangements and intrinsic flexibility may produce a broad range of conformations. So, if your protein is structurally flexible, this is the intrinsic property of the protein, it could produce different conformations. In the case of conformational variation and in some cases of compositional heterogeneity, solution buffer conditions can dramatically alter the appearance of a sample in the microscope. So, in those conditions, to bring the homogeneity, which is a critical condition to make the cryo-electron microscopy experiment successful, you have to screen with different buffers and you could see dramatic changes in the result, in the homogeneity profile of the protein. For those samples before working, a high throughput screening can be used to identify optimal buffer compositions. Chemical cross linking may also be a useful tool for reducing sample heterogeneity. Methods such as graphics have been developed that permit the purification of a sample based on stoichiometry. However, The chemical cross-linking may introduce artifacts such as trapping the complex in a non-native or non-functional form. So, as I was talking from the initial stage, the correlation between the sequence and function have to be done by structure, but to do that the structure have to show the information, provide the information about the native state, and that is one of the problem we are always discussing in case of crystallography. We do the crystallization in very high concentration of salt and all, and we call this condition not native condition, we call it in crystallo condition. So, if you want to apply chemical cross linking in case of cryo, you are actually giving opportunity to such type of artifacts to come. Your chemical cross linking might introduce artifacts, and we do not want to do that, but sometime the complex is so unstable we have to do it. It is always a loss and gain problem, like you have to keep trying. Other approaches to reducing conformational flexibility include ligand induced stabilization, which we talked about. When ligand comes, ligand bind with the protein and stabilize it, where molecules such as a substrate, ligand, inhibitor or protein nucleic acid binding partners. Formation of those complexes can promote stable complex formation, as I talked about, a strategy that is well established in X-ray crystallography already. When we talked about X-ray, we talked about these stabilization factors. Typical uses of common grid preparation method. There are different one. Negative staining visualization, this is a grid preparation method. So, you have different methods: negative staining visualization, negative staining reconstruction, cryogenic visualization, cryogenic reconstruction when you go to a single particle, cryogenic reconstruction in case of tomography. So, for negative staining visualization, the typical samples are macromolecular complexes greater than 50 kilodalton, organelles, prokaryotic cells. For negative staining reconstruction, macromolecular complexes that appear reasonably homogeneous. For cryogenic visualization, macromolecular complexes greater than 150 kilodalton, liposomes, organelles, prokaryotic and eukaryotic cells. For cryogenic reconstruction for single particle, macromolecular complexes greater than 150 kilodalton. For cryogenic reconstruction tomography, organelles, prokaryotic cells, thin edge or lamellar of eukaryotic cells. Typical equipment for negative staining visualization: electron microscopy with tungsten filament, negative staining reconstruction, electron microscopy with LAB6 filament CCD detector. Cryogenic visualization, EM with LAB6 or FEG filament, we would talk about them, CCD or DED, and cryo holder and sample transfer stations. For cryogenic reconstruction, as cryogenic visualization, DED preferred, we will talk about. Cryogenic reconstruction, as cryogenic visualization, DED preferred, energy filters and phase plates can be of great benefit. Typical results for negative staining visualization: visualization of specimen with high contrast. For negative staining reconstruction, resolution limited by the grain size of specimen, typically to 20 angstrom at best. Cryogenic visualization, the typical result is visualization of specimen with low contrast. Cryogenic reconstruction for single particle, depending on the specimen, reconstruction of 3 to 20 angstrom, we are going towards high resolution. Cryogenic reconstruction for tomography, resolution of tomographs less than 10 nanometer, sub tomogram averaging can produce reconstruction of around 10 angstrom. Auxiliary equipment for negative staining visualization: glow discharge unit, UV lamp for treating carbon surfaces. for negative staining reconstruction, software and computer hardware to process data, for cryogenic visualization, software and computer hardware to process data, cryogenic reconstruction, time resolved electron microscopy. We will talk about this in the next class. In the spatial instrumentation, cryogenic reconstruction, CLEM, this is also special type of laser electron microscopy. We will talk about FIB milling, we will talk about that, or HPF and sectioning where sample is too thick for direct visualization. Other consequences which is of special mention for negative staining visualization, different stains such as uranyl acetate or ammonium molybdate may be optimal for different specimen. Some sample buffers may cause problems including presence of detergent, phosphate reducing agent or glycerol. Sample may become deformed by the stain and sometimes it have severe effect. Sample may adopt preferred orientation on the carbon. Optimized stain depth is important for obtaining the best results. For cryogenic visualization, specimen contrast is low compared with negatively stained samples. Sample buffer components can reduce specimen contrast such as glycerol, sucrose and detergents. Vitrification. Vitrification is a process which is a key to cryo. We will talk about that. Vitrification process may require optimization for best results including optimizing blotting conditions and support films. When a thin continuous carbon support film is used, sample may adopt preferred orientation on the carbon. So, we need the thin continuous carbon support film sometime when it is not getting the optimized conformation. Samples smaller than 500 kilodalton can be very challenging to visualize with cryogenic visualization. Typically, sample must be 10 to 50x more concentrated than used in negative stain visualization to achieve similar particle distribution. Coming to cryogenic reconstruction, for single molecule, support film can dramatically influence particle distribution. So, support film is important. A continuous carbon film can aid particle distribution, but this can introduce preferred particle orientation and noise into the image. For tomography, use support films with 200 mesh size to allow high tilt. Additional gold fiducial markers may be helpful to aid ailment of tilt series images when you are going to collect the tilt images and from there calculate the angular positions and reconstruct the 3D image. Preparation of the grid. Once the specimen is ready, it must be prepared from imaging by electron microscopy. To image with electron, a microscope is maintained under a very high vacuum in which hydrated biological specimen would dehydrate rapidly. So, this is a very big problem. Thus, to image a biological specimen, it must be fixed, preferably in a native or native like state. Another consideration is sample thickness. In some cases, the sample may be too thick for electrons to be transmitted, a prerequisite for transmission electron microscopy. And so, the specimen may need to be processed to make it thinner. It needs sectioning in these cases. The choice of preparation technique is ultimately determined by the nature of the sample and the resolution required for the intended biological insight, but common methods include negative staining, plastic embedding, sectioning and vitrification. EM grids are traditionally 3.05 millimeter across and made from a mesh of metals such as copper, gold, nickel, molybdenum or rhodium. Most commonly used grids are copper grids, but gold supports are becoming more common, especially when cells are to be grown directly onto the grid, as the gold supports they are non-toxic to the cells. The metal mesh supports the film on top, the mesh size or number of squares across the grid is defined as the number of square in 1 inch. For example, a 200 mesh grid has 20 square across in each direction and a 300 mesh have 30 squares. So, in that way they are sections, so that you could understand the position, you could put them and you record that. 200 to 400 mesh grid are most commonly used for cryo-EM. Over the metal support, a support film is deposited. Different support films are used for different purposes. Finer mesh sides provide more support for the film, but when the grid is tilted, the bars can block the beam. Therefore, 200 mesh grids are most commonly used for tilt series data collection. So, any type of mesh grids could be used, but for tilting experiment you have a optimization, and there 200 mesh grid work the best. So, this is about the grid preparation. We come to negative staining. Summarizing it, typical uses of negative staining: the high contrast and speed of grid preparation of negative stain samples makes it ideal for assessing sample purity, concentration, heterogeneity and conformational flexibility. So, by doing negative staining, we could very quickly see the standard or assess the sample quality. Low resolution 3D constructions from stained data can also provide starting model for higher resolution cryo-EM studies. Advantages: high speed of sample preparation and good specimen contrast. Additionally, there is the ability to label with antibodies or gold to further aid functional studies and determine stoichiometry. Grid can be easily kept for many years and re-imaged. Disadvantages: structures limited to modest resolution around 20 angstrom, surface topology only, possibility of staining artifacts incompatible with some buffers or reagents. Negative stain is a common method for examining a specimen, especially macromolecular complex at room temperature. It is a common method, it is the most common method. Many variations of the negative staining technique have been documented since the late 1950s using several different heavy metal stains. Typically, specimens are adsorbed onto a thin 10 nanometer continuous carbon support film that has been rendered hydrophilic. It is then stained with a solution of heavy metal salt, commonly 1 to 2% weight by volume, uranyl acetate or uranyl formate, and blotted to ensure a thin layer of stain with no stain migrating to the back side of the grid. So, you have the grid, you have the staining and you just transfer it. We will see how it works. Some common buffer components are known to adversely affect the quality of the staining. However, a large dilution of a concentrated specimen with a compatible buffer immediately prior to application to the grid is the easiest way to ameliorate this. If this is not possible, washing the grid prior to staining is also an option. Like when you will always try to set up it in that way that you have a grid, you have the stain and it does not go in the other side. But how you could do that? One is dilution, proper dilution, but if it is not possible, then wash it properly. The staining process quickly dehydrates the specimen and envelops it in stain, where the sample is visualized by the absence of stain. Negative staining occurs where the sample itself becomes stained, positive staining occurs. So, if you see here, the whole thing is stained, the gray color, this is the stain. So, whole thing is stained and not the sample. So, sample is unstained, negative staining, but here this is the periphery. So, here the sample is not stained. Here sample is stained. So, this is positive staining. The resulting shell of heavy metal atoms generate amplitude contrast and a relatively high signal to noise ratio, which you see the image in that. The correct stain depth must be achieved for optimal imaging, with information being lost when the stain is too deep or too shallow, you do not get the depth. The dehydration of the specimen and its deformation during adsorption are drawbacks of negative stain sample preparation. So, one is the possibility of dehydration and deformation. Additionally, the resolution of the stained image is limited by the grain size of the stain, which determines how well the stain envelope reflects the structure of the object. The use of a continuous carbon support film can result in samples adopting a preferred orientation on the grid, complicating 3D structure determination due to a lack of views. Despite these problems, negative stain sample can generate 3D data and provide invaluable biological insight. For example, negative staining can be used to elucidate the binding of small molecule inhibitors in a matter of weeks, assess conformational changes, complex stability and subunit stoichiometry or position. So, you get informations of biological interactions. Negative staining can also be combined with vitrification. We will talk about that in a sample preparation technique known as cryo negative staining, which we talked about in the general principle. This method combines the high contrast of using a heavy metal stain with the protective effect of cryogenic preservation. So, you use a heavy metal stain, but then you have the low temperature. So, the effect is protected. Vitrification, as I told, one of the key concept where the cryo-electron microscopy works is vitrification. This is sample preparation techniques such as staining and plastic embedding involve the dehydration of biological specimens, which fundamentally removes them from their native aqueous environment, which we do not want. The normal sample preparation procedure where the preparation methodology is pushing us away from the achievement of native condition, we are getting non-native condition, we do not want that. So, cryo immobilization preserves that aqueous environment whilst also ameliorating radiation damage. So, I will talk in the discussion part, but you definitely understand with the higher mass electrons are making radiation damage, especially in biological sample, the radiation damage is really critical. So, with the development of cryo immobilization, it preserves the aqueous environment, the native solution environment which we want the reaction or the information to get, and the reduction of the radiation damage. Imaging of cryogenically immobilized sample by electron microscopy is known as cryo. As I told, this is the one which gives the identity of cryo, the identity of cryo to work with the biological samples. Same they were working with materials for long time, they are so good, they are so high resolution, but we could not have include the biological samples to perform TEM and SEM because of the radiation damage is one of the major issue. By doing this cryogenic immobilization, that makes cryo today's cryo. In the next class, when I am talking about how the high resolution which we are getting today, how they achieve it, one of the main reason is this. The sample must be frozen extremely rapidly at a rate of 10 to the power 6 degree centigrade per second. so that the water in and surrounding the specimen is fixed in a vitreous state, that is called vitrification. If freezing occurs too slowly or the specimen is subsequently warmed above minus 137 degree centigrade, the temperature at which water devitrifies, crystalline ice is formed. According to the experienced users, warming the sample more than minus 160 degree centigrade can give poor quality ice, affecting greatly the experimental data. Ice contamination compromises the structural integrity of the specimen as crystal withdraw water molecule from the hydration cell of the specimen or the specimen itself. Formation of crystalline ice also degrades image quality as they diffract electrons. So, the ice they become crystal, so they start diffracting the electrons, again creating another complication. Contamination can also occur during the freezing process, such as hexagonal ice, which can be reduced by working in humidity control environments and minimizing ice contamination in the liquid nitrogen. It could come from the liquid nitrogen which is used for the freezing. So, you see here these are some of the conditions. Although cryo EM has been in development since the 1970s, the large number of high resolution structure deposited in the last 2 years has promoted increased interest in the technique. As you see here, good vitrification happened. Here you see the presence of crystals. Here you clearly see the hexagonal crystal impurity or contaminant. Here you see the dots, these are formation of the kind of non-homogeneous condition. So, we talked about sample preparation, we talk about negative staining, we talk about vitrification. How we could bring the vitrification? One of the method is plunge freezing. A wide range of sample from small 150 kilodalton macromolecules to whole eukaryotic cells can be vitrified and imaged by cryo using plunge freezing technique. Sample is visualized in a native like state. Processing of data can yield high resolution 3D structural information can be obtained with ease, with comfort. Disadvantage: biological sample must be imaged with low electron doses to prevent radiation damage resulting in poor contrast. It is sometimes non-trivial to optimize sample distribution and ice thickness. So, when you have thin specimens such as suspension of macromolecules, 2D or very small 3D crystals, small cells and the thin edge of the larger cells, cryo immobilization can be achieved by blotting to generate a thin film of liquid containing the sample and then rapidly freezing it by plunging into a cryogen. So, you have the thin film, you do the blotting and freeze it rapidly. The most widely used cryogens are liquid ethane or propane cooled by liquid nitrogen. Liquid ethane or propane cooled by liquid nitrogen. Plunge freezing thin sample is used for a wide range of specimens. For each, the ice layer should be as thin as possible without distorting the specimen and whilst fully embedding the particle to maximize the sample contrast. Failure to fully embed the specimen can lead to preferential radiation damage, because if you could not embed it, there would be radiation damage of the specimen outside of the ice layer. Blotting and plunging can be achieved with simple devices often built in house for your own requirement. However, these devices often struggle to provide consistent results within and between batches of grids prepared. Several commercial instruments are available that achieve more reproducible results, including models by FEI, Leica and Gatan. Commercially available freezing apparatus offer different features that may be beneficial when working with certain samples. For example, single sided blotting may be advantageous when preparing grids of adherent cells, because otherwise adhesion property would be problem. Double sided blotting can result in the stripping of some cells from the grid and onto the blotting paper. Single sided blotting can be performed from the back side of the grid where cells are not adhered, circumventing the problem caused by double sided blotting. Additionally, some macromolecular complexes may benefit from a low around 5 degree centigrade temperature or humidity control in the freezing chamber. These considerations may influence the choice of freezing apparatus where the choice is available to you or not. So, as I told, there are mostly 3 popular commercially available plunge freezing devices: Leica EMGP electron microscope, Grattan Cryo Plunge 3 and FEI Vitrobot. So, in Leica the humidity control in the chamber is present, it is also present in FEI Vitrobot, but in Grattan Cryo Plunge 3 it is not present, the chamber always set at 98% humidity. Temperature control in the chamber is present in Leica and also in FEI Vitrobot, but it is not present in Grattan, it operates at ambient temperature. Automatic control of ethane temperature is present in Leica, present in Grattan, but absent in Vitrobot. Blotting modality, single sided, as we have seen that single sideds are advantageous in many cases. Grattan single and double sided depending on the requirement, and Vitrobot double sided. Some specialty for Leica, optional stereo microscope to monitor blotting, it is a additional facility. Grattan removable humidity chamber, as the chamber is set at 98 degree, if required it could be removed. For Vitrobot, currently the most common plunge freezing device, it is the mostly used. So, this is different scenarios where plunge freezing is used for eukaryotic cell, prokaryotic cell, isolated organelles, synthetic liposomes, viruses, macromolecular complexes more than 100 kilodalton. You see the image after plunge freezing. We talked about plunge freezing. Plunge freezing is mostly applicable to thin samples. Whenever your sample is thick, you need high pressure freezing. Thick specimens such as the nuclear region of eukaryotic cell, tissue sections and whole organisms such as C. elegans that cannot be prepared by plunge freezing, they are going under high pressure freezing. Advantage: the sample is preserved in a native like state, can result in high resolution 3D structural information. Disadvantage: to be visualized by TEM, that is become electron transparent, the sample must be sectioned or thinned by focus ion beam or FIB milling after freezing. So, sectioning is required. There is the potential to generate artifacts in this process, and it can be technically challenging to make the sectioning after the freezing. While samples thinner than the edge of a large cell may be vitrified by plunge freezing, thicker samples such as nuclear and perinuclear regions of eukaryotic cells or tissue sections are likely to experience some crystalline ice formation during plunge freezing because of the thickness of the sample. For these specimens, high pressure freezing HPF is an effective alternative. High pressure freezing. High pressure freezing or HPF involves raising the pressure of the sample to 2000 bar while dropping the temperature using liquid nitrogen. So, the low temperature is achieved by making the pressure hugely high, around 2000 bar. For samples which are around or greater than 100 micrometer thick up to 300 micrometer thick, they can be vitrified using high pressure freezing, but must be subsequently sectioned to thin enough for transmission electron microscopy. Sectioning can be performed under cryogenic condition, which gives the best preservation of the sample. This technique is known as cryo electron microscopy of vitreous section or CEMOVIS, uses cryo ultramicrotomy with a diamond knife to produce sections 40 to 100 nanometer thick. So, a special system which use cryo ultramicrotomy using a diamond knife to produce 40 to 100 nanometer thick sections. High pressure freezing is a useful technique capable of imaging thick specimen in a native like state, but it is technically extremely challenging. A common alternative approach is to perform freeze substitution on the sample, which enables sectioning and imaging at room temperature. Freeze substitution involves gradually warming the specimen and replacing the water with acetone. The sample can then be stained, embedded in resin and sectioned. Freeze substitution introduces fewer artifacts than traditional plastic embedding, but small ice crystals do form, causing rearrangement of cell structures, and staining is not uniform. So, interpreting images can be very challenging. An alternative to sectioning, the use of FIB milling to reduce specimen thickness. FIB milling is carried out on frozen hydrated specimens in dual beam scanning, electron microscopy and FIB instrument. A focused beam of ion is rested across the surface of the sample, removing surface atom in a process known as sputtering. The scanning electron microscope allows simultaneous non-destructive monitoring of the milling process. Gallium ions are commonly used because of their volatility and low melting point. If you remember, I was talking about liquid gallium. Liquid gallium is used as the target in X-ray crystallography. The ion beam is generated by a liquid metal ion source and liberated by an extraction electrode. Electromagnetic lenses and apertures are used to focus the ion beam, and deflectors to control the pattern of milling. FIB milling can introduce artifact, as sputtered material can redeposit on the surface of the specimen, although an appropriately positioned cooled anti-contaminated device can reduce this effect. Differential milling rates can also produce streaking or cutting across the surface, and local heating devitrification can also happen. However, conditions have been established where temperatures do not rise enough for this to be a routine problem. Specific steps can be taken to ensure a smooth surface during milling, such as use of gas injection system to create a organometallic platinum layer covering the specimen that protects it from some artifacts caused by irregular sputtering during milling. FIB milling can either be used in conjunction with imaging by SEM, as in serial block face imaging, or the milled sample transferred to the transmission electron microscopy. Since the first successful cryo FIB experiment in 2003, workflows have been developed to improve and optimize the technique, including in situ cryolamellar preparation of cells grown on EM grids. Cryo FIB technology is still developing. One particularly exciting development is the implementation of correlative light microscopy in combination with FIB milling. We will talk about special instrumentation in the next class. Now, I will talk about imaging. So, we have the sample preparation, we do the staining, then we go for freezing, and now it is imaging. The optimal hardware for electron microscopy is highly dependent on the imaging experiments planned. There is often a trade off between performance, cost, convenience and the availability of the instrument time, because we all know that it is very expensive. Here I am trying to discuss the choices of electron source, electron detector and hardware to boost signal to noise ratio in the images. What are the instrumentation and what it is affecting? Electron source very commonly uses the electron gun or field emission gun FEG. So, the electron gun of an electron microscope extracts and accelerates electron and is typically either a thermo-ionic electron source or a field assisted thermionic emitter such as Schottky emission gun. They are commonly known as field emission gun or FEG. Common conventional thermionic sources include tungsten filaments or lanthanum hexaboride crystals LaB6, which we discussed earlier, which are heated so the voltage potential exceeds the work function required to liberate the electrons and operate at voltage between 80 to 200 kilovolt. By comparison, a field emission gun is an extremely fine tungsten filament coated with zirconium oxide, typically operated at extraction voltage of 200 to 300 kilovolt and at 1800 Kelvin, which means 1526 degree centigrade. Field emission guns are much brighter and more coherent compared with conventional thermionic sources and so are preferred for high resolution EM studies. However, they are significantly more expensive both to purchase and also to maintain. The choice of gun should therefore reflect the experiment to be carried out. For example, negative stain electron microscopy does not require the brightness and coherence of a field emission gun source. Coming to electron detectors, so we have the source now, we have to detect the high energy electrons used in the electron microscopy imaging are recorded using a detector. Recording device include photographic film, charge coupled device, cameras or direct electron detectors. So, the photographic film, the CCDs we have already discussed when we are discussing the X-ray crystallography detection and they are same, but direct electron detectors are something new. Cryo EM images of biological specimens are intrinsically noisy due to the low electron doses used to prevent specimen radiation damage. A perfect detector would add no noise, but in practice all detectors actually do that. This can be expressed, the noise or the effect of noise expressed as the detective quantum efficiency or DQE of the detector, the square of the output signal to noise ratio SNRO, which is over the input signal to noise ratio SNRI. So, SNRO is signal to noise ratio of the output signal to the SNRI is the input signal to noise. So, a perfect detector would have a DQE of 1 across all spatial frequencies, DQE equal to the ratio of SNRO signal to noise of output square by input square. Historically, film was used for electron microscopy data collection due to its large field of view and extremely small pixel. Okay. However, recording large data set using film is inconvenient and time consuming, is the same thing we discussed in X-ray crystallography. Film emulsion contains water and introduces contamination into the column of the electron microscope and thus requires desiccation before loading an anti-contamination devices within the microscope, which is not a user friendly method. Use of film is also limited the number of images which could be collected in a day's data collection to around 100 Film must also be developed and digitized using an extremely accurate and thus expensive densitometer. CCD cameras were developed as a more convenient solution. The same thing again I told we have talked about in X-ray crystallography, which also enabled the development of automated microscope alignment and image acquisition procedures, as well as significantly improving the ability to collect a tilt series. CCDs utilize a phosphor or similar scintillator which induces the emission of photons when electrons strike it. The CCD camera then transforms these photons into electrical signals. A CCD chip has an array of photosensitive elements. I have shown you the details of that, in which electrical charge accumulates. Charge is transferred to readout register, amplified and digitized to form an image. The DQE of a CCD camera is inferior to film at the electron energies typically used for imaging. The scintillator layer results in electron and thus photon scattering, causes a loss in the sensitivity as well as introducing an accelerating voltage dependent point spread function. Despite those problems, the data collected on a CCD camera under appropriate imaging condition can be processed to sub nanometer resolution. So, that is a advantage. Coming to our kind of last topic, the automated data collection. The signal to noise ratio of cryo-electron microscopy images is very low, and so many images of individual particle greater than 1000 are usually needed to generate the structure using single particle processing method. So, more images you could collect, better resolution you are going to get. The number of micrographs required is highly variable and dependent on the specimen, for example, its size, its adoption of preferred orientation and symmetry. The number of particles per micrograph, desired resolution and levels of heterogeneity, all you need in the data set. As a result, several software packages have been developed to automate data collection and make more efficient use of microscope time. One commonly used package is FEI's automated data collection software EPU or E Pluribus Unum. Open source programs are also available with similar functionality such as Leginon, Tom, 2 and Serial EM. Software to allow the automated collection of tilt series, as we have discussed, the tilt series with angular data is important. So, also been developed including Serial EM, UCSF, Tomo, Explore 3D and Leginon. Efforts are also underway to introduce semi-automated data processing pipelines for the cryo-electron microscopy data. So, we have covered the basic functionalities and the process involved in that. So, if you see here, you have a protein sample which contains the macromolecules. This is the grid, it is blotted as I talked about, then the grid is put in the freezer and it is plunge frozen, and now it is time to data collection. You see that this is the cryo-electron microscope, electron is coming, you see, and then it hits the sample and the data is coming. You see the data is oriented in different direction. The software actually make the alignment similar oriented data with in similar position, and then all those similar data is kind of coming together and your 3D model is ready. This is the 3D model you prepare for a macromolecule. So, in cryo-electron you have electron microscopy, the first one, to the proper grids, vitrification, different methods of freezing and all, data collection where a lot of automation is going on, and last but not the least, data analysis. We will talk about few of this section into more details, and we will also discuss the history how cryo EM is actually proceeding and the next class, and we will also talk about the data analysis part which I did not talk about today. Thank you very much. Again, as I say every time, please keep listening and keep asking questions. Thank you very much for listening. Thank you.